Well, good evening and welcome to the Birch Aquarium. My name is Nigella Hilgarth and I'm the Executive Director here at the Birch Aquarium. It's my great pleasure this evening to introduce our speaker, Dr. Lynn Talley. Now, I have to tell you that Lynn graduated with a PhD in 1982 from physical oceanography from Woods Hole. But we don't hold that against her, as you know. But she's been a professor here of oceanography actually since '84. And she's a member of the physical oceanography and climate curricular groups and is a very, very distinguished scientist. But before I go into her work a little further, I also just want you to know that she had a BA in physics and in piano, or BM in piano, rather. So she's really very accomplished in a variety of ways. Now, her main research interest is in large-scale water mass distributions and the circulation of the world's ocean. So she's interested in the way that water moves on a really massive scale around the oceans of the world. And that includes the formation of intermediate water masses and observations useful for understanding the large-scale dynamical processes common to most ocean basins. She's a seagoing oceanographer. It may surprise some of you to know that not all oceanographers go to sea. So I think it's important to know that she has actually been on 12 hydrographic cruises in the Atlantic, Pacific, and Indian Oceans, and many of those were part of the world circulation experiment to understand the ocean circulations better. And her current projects include studies in the southeastern Pacific and near the Gulf Stream. She has numerous awards and numerous publications, has served on many, many boards, and in fact is highly distinguished. I don't want to use any more of the evening up in telling you all the amazing things that she's done. So without any further ado, I'd like to introduce Lynn, who's going to talk on tracking the ocean-climate connection.
Hello, friends and new friends. Very happy to be here tonight. Very soon after the release of the IPCC Summary for Policymakers, and so a lot of the talk I'm going to give tonight won't be just a review of what's going on in the ocean, but I'm going to start out with a pretty big focus on what the IPCC, the Intergovernmental Panel for Climate Change, has said about climate and about how oceans are changing. So my very first slide, I couldn't resist. This was a wonderful image from the New York Times cover page about a week ago. There are the polar bears. They're kind of like us. They look out there and there's a, well, maybe it's changing around here, but yeah, who cares to anybody else? It cares a lot to me, this polar bear, but is it changing elsewhere? What I hope to give you is a really big picture. The ocean is an amazing recorder of climate change, and it's one of the main sources of the databases that the IPCC has used to make conclusions about climate change. Down in the right corner is a West Virginia coal miner. West Virginia is kind of my roots. And he's got a canary. Canaries and coal mines. Coal mines, we burn fossil fuels, we make CO2. That's a big problem. Coal mines have methane. Methane is also a greenhouse gas. Methane's what explodes. That's why you have canaries, to find out if there's methane in the mine if you're a coal miner. So it's kind of very hackneyed kind of picture, but we're going to talk about a lot of the canaries in the coal mines of climate tonight. So onward, these are kind of the regional things that you and I might see out there. Changes in glaciers. Are they really related to anything important? Here's the Muir Glacier, 1941. Here it is in 2004. Just go back and forth if we can. That's one glacier. There are many glaciers doing this. There are a lot of different signatures around the world of climate change. So those are kind of the things that we can see. The ocean is really large. It's really out there. Mostly we see it rather remotely. And so we have to be able better to visualize these big databases. I'm going to mix together results from the Intergovernmental Panel on Climate Change, IPCC. Working Group 1 is the scientific basis for climate change. That's the report that came out, the summary that came out last week. I'm also going to show you results that have to do with that, but they're my own presentation, and because of IPCC rules, which I had the fortune to be participating in, I have to be very careful to separate what's released and what's a personal review of the field. So I'm going to try to keep those separate. First part, I'm going to keep them separate in the presentation. Summary for policymakers, highlights, which include the oceans and a lot more than the oceans. And then the second part is more of a review of changes in ocean heat content, ocean sea level, and distribution of salinity, which is a really good indicator of changes in rain, evaporation. We expect big changes, big dislocations, changes not in patterns, but intensity of evaporation and rain and precipitation as we go into global change. So we'll talk about how we observe the ocean. Are these properties changing? Obviously they are if I'm going to show them. And do the changes mean anything? So first of all, the IPCC, physical science basis. The IPCC, this is the fourth assessment report. It's the fourth time that the community of scientists, climate scientists in the world has gotten together. I'm part of Working Group 1, the physical science basis for climate change. The summary was released last Friday or Thursday. I highly recommend downloading it. There's the website. It should be accessible to anyone here. You can read it. You can see what it says. The remainder of the details will come out in May. There are two other working groups, one on impacts, adaptation, and vulnerability, that's coming out soon, and one on mitigation of climate change. Our portion, the science portion, has nothing to do with policy. Our leader, Susan Solomon, likes to say we're policy neutral, not policy prescriptive. It's really important to stay out of policy. We just say what's occurring and what is projected to occur. The science in the IPCC, you can break into two parts: observations, which show climate change or not, and projections using models, many models. Highlights of the summary for policymakers. The first of all, this is the forcing. You've seen this one if you went to see Al Gore's movie, Inconvenient Truth, that these curves of, I guess I have this pointer going here. This is good. This works. This is carbon dioxide in the atmosphere. There it is back 10,000 years. Here we are. Pshoom. Okay, you saw that in his elevator in the movie. Methane, same thing, up. There's been a little leveling off recently. Nitrous oxide, the third one that's tracked closely, same thing. Greenhouse gases have gone up. No question that that's due to human activity. Does that have any impact on climate? That's the big question. Next point is that the understanding of warming and cooling due to man has improved since the third time this was done. That was 5 years ago. This leads to very high confidence. That means 90% likelihood that the globally average net effect of human activities has been one of warming. And that's broken into a quantity that has to do with how much extra energy hits each meter of the surface. And my colleague Ramanathan can translate that into a number of 60-watt light bulbs, like trillions of them. I don't remember the number. It's a lot of light bulbs. One thing that can be done, and it's done in the summary, is to break that warming into each piece. How much is due to CO2? How much is due to methane? How much is due to freons? How much is due to changes in clouds? This is ozone. How much is aerosols and all these other things? There are some negative effects on the heating part. The sum comes up to this 1.6. And then there's an error bar on that. And the error bar sits above 0. And that's the basis of the claim, the conclusion that we are warming the planet. Another highlight. Warming is unequivocal. There's no question that it is warming. This is a record of global mean temperature from 1850 to the present. Here we are up here, and we keep on going. Global average sea level has been rising. Northern hemisphere snow cover is going down. Those are, and the error bars are shown in blue here. There's no question these things are happening. Other points without figures, because I'm only using figures that are in this summary. There have been long-term changes in climate at all these different scales. So that includes those polar bears and the glaciers. Changes in Arctic temperatures. Arctic is the place that's responding the most dramatically. Changes in precipitation, salinity, wind patterns, etc. Droughts, heavy precipitation, heat waves, intensity of tropical cyclones. not frequency, just intensity of hurricanes. Some aspects of climate have not been observed to change. That may mean that they are changing, but the changes are so far too small to detect above natural variability or above the ability of the observing system to see them. So there are a number of things that people kind of curious about and think about. Tornadoes. Are those tornadoes due to climate change? Well, no good guess on that yet. Projections. For the next 2 decades, no matter what, there'll be a warming of about 0.2 degrees centigrade per decade. That's actually if we continue emitting greenhouse gases as we do now. Hard to imagine any change in that in the next 20 years. So there's an expectation of continued warming, and that's the rate that it will happen at. And if greenhouse gas emissions are continued at current rates, that induces further warming and many more changes that are likely larger than have been observed so far. And then there's a whole bunch of curves down here. These are for model runs out to the year 2100. Lots of different scenarios, how much emissions, how much economic growth. Are people smart? Are they stupid? Kind of all built in. They don't say that, but they're sort of. And then there's one down here that if you cut emissions completely right now today, this is what would happen. A slow, steady increase in temperature. But, we probably won't, so it probably goes up. I'm going to skip down through this. You can read all this in the paper. We're going to keep on seeing changes in temperature. The last one's been a big subject of the media. The Greenland ice sheet. Some of the scientists said, wait a minute, you're way under projecting what's going to happen if the Greenland ice sheet breaks up. I'd like to say that the IPCC is inherently an extremely conservative process, really, really heavily reviewed, nothing published without error bars, nothing published out without a lot of consensus. Every word that's written has 5 comments on it, I'll tell you for sure. And every comment has to be answered. It's very heavily vetted. There is a Greenland ice sheet. It's likely to melt at the, given the temperature increase that we are probably headed for, it will melt. If it melted from the top down slowly, we get 7 meters of sea level rise after about 1,000 years. That's the conservative projection. So all the new stuff is, well, maybe it won't take 1,000 years. I'll show a couple alarming slides, but those are just alarming and personal later. Okay, let's look at the oceans in the summary for policymaker. First of all, temperature and heat observations that go into understanding climate change. There's widespread warming of the upper several hundred meters of the ocean, and that is part of the evidence for the climate change. We have seen that the average temperature of the global ocean has increased down to depths of at least 3,000 meters. More than 80%, possibly 90% of the heat that goes into our system and stays trapped is in the ocean. So the ocean is a really important place to measure. It's a canary. It's not necessarily part of how it is part somewhat of how the whole thing responds, but here we're just going to focus on, that's our measurement. We saw it warm. These are projections of climate change. I just focus on these right panels because it's easier to see the color from back there. Really poor graphics that you can pull out of this summary. In the year 2100, these are 3 different projections for temperature change in the world. Reds and yellows are all increases. There's no place where it's projected to go down. The most likely scenario is the one in the middle. Most intense colors in the Arctic and over land. The oceans actually would be not cooling, but warming only a little bit in the Southern Ocean and the North Atlantic. That has to do with the circulation of the ocean, especially this one up in the North Atlantic. We'll understand that in a few slides down in why this one is a little bit less than the areas around it. Nevertheless, basically the whole globe warming. Sea ice is projected to shrink in both the Arctic and the Antarctic in all scenarios. The SRES is for the emissions, how much emissions there are. In some of these projections, the late summer sea ice in the Arctic will disappear. This seems to be a robust projection. It doesn't say that it's disappearing in winter. There'll still be seasonal sea ice. It'll just be, we won't have all that multi-year pack ice up there. These pictures are not from the IPCC. This is just off of the NASA website. Here's the Arctic ice in 1990. Here it is in 1999. There's been measurable decrease in the sea ice cover. If you take 2 snapshots, you might not believe that there's change. But if you put together a credible inventory of how much ice there is, it's been declining. Second thing about the oceans in the IPCC, sea level projections. Here's the rise in sea level since 1850. It's gone up 20 centimeters. That's 8 inches since 1870. That's measured. So we have had an increase in sea level. It's attributed to, this is a really poorly, hard to read table out of there. There's a nice graph buried somewhere else that I can't show. The biggest contribution to the sea level rise is thermal expansion. What does that mean? You heat water, it expands. Most of what's going on is the heat's going into the ocean, and the ocean expands a little bit. 8 inches, it's only that much. They go, oh, that's not going to endanger my beachfront home or my cliff or anything, but you start projecting this into the future and you get some much larger rises. Thermal expansion is the biggest. Melting of glaciers and ice caps in the last 10 years has been about half that size. Greenland ice sheet and Antarctic ice sheets, measurable. Melts of ice, and that's adding to sea level rise. So basically, two contributions. One is expansion of the water due to the heat, and the other is just dumping more water in from melting land ice. You have to melt land ice to get sea level rise. If you melt sea ice, nothing happens. It's already floating on the ocean. If you take your glass of water with ice in it, as the ice melts, the level of the water doesn't change. It's sort of there. That's Greeks discovered that. If you melt sea ice, nothing happens. You just dump. Actually, sea ice is fresh. It loses its salt as it freezes. And so it's important for the salinity of the ocean, because as it melts off, it's leaving kind of a fresh layer around, and the salt that had dripped out of it before lands somewhere else. That's an interest I have for water mass formation. But it doesn't contribute to sea level rise. But it is important for the global climate, because as you remove ice, you remove the ability to reflect the sun. That's a really big important thing. The sun reflects off of ice and snow. You melt the ice off, you don't have that reflection, and you get kind of a positive feedback. It gets warmer. Okay, the last 10 years, 1.2 inches of sea level rise. This translates to a foot over the next 100 years. That's the projection for sea level. Ice sheet melting. Ice core data showing that polar temperatures way back 125,000 years ago were 3 to 5 degrees higher than now. That's where we're projected to be going, 3 to 5 degrees higher. And in that case, you melt off all of Greenland. You don't melt off all of Antarctica. You do melt off all of Greenland, and you get quite a few meters of additional sea level. Something else in the IPCC summary for policymakers, it's not exactly the ocean, but it's important to the ocean, because the oceans are forced by the winds. So if the wind changes, the ocean circulation changes, and how things like CO2 can get into the ocean would change. So one cares as an oceanographer about the winds. An observation is that mid-latitude westerly winds have strengthened in both hemispheres since the 1960s. That means the jet streams up there are stronger now. There's also an observation that they have been moving poleward. They're getting stronger and shrinking towards the poles. So that changes the wind forcing kind of the higher latitudes. It's projected that these storm tracks will move poleward. We're not talking about a lot, several hundred kilometers, but that's a big dislocation for climate. Oops, that should say broad, not BORAD, the BORAD pattern. Borax, okay. Third, on the topic of salinity, which is real important for us water mass people, precipitation and evaporation will change as the world warms. And we already see a suggestion of a change in precipitation and evaporation because we oceanographers have measured salinity for a long time. It's really, really hard to measure time series of global precipitation evaporation from the atmosphere. It's so noisy, it's so patchy. But if you measure ocean salinity, which is 75% of the globe is the ocean, you can see changes in how salty it is and how fresh it is. It's kind of an integrator, it adds it up. We're going to see, this is a picture of the projection of precipitation in the year 2100. Brown means it's drier. You see all the dry areas are getting drier. Blue means it's wetter. All the wet areas get wetter. So basically what's happening is you're pulling, because it's warmer, you can put more water vapor into the atmosphere. it sucks up more. It's warm, you know, tropical is moist. So you get more water up there and it's moving around more water. So you're evaporating more in the evaporating areas and dumping more in the rainy areas. So in a dry area, we're on the edge of a dry area here. We might get drier. Down towards Mexico, really drier. Up in the northwest, Canada, a lot more precipitation. That's where you don't want to buy your house. Maybe I'll go for Pismo Beach. No. Someplace in the middle. Another area for the summary for the oceans, in the summary for policymakers, meridional overturning circulation. This is a mouthful. Maybe some of you have been coming to these lectures and know what this means. What this means is that the ocean, here's a nice diagram down here, which is not in the IPCC. This is your global conveyor belt picture. You might have seen that in Day After Tomorrow movie. We won't parse that either, but you know, it was nice. Hollywood, you know, wrong science, but you got the picture of this. Water moving north in the North Atlantic, sinking in off of Greenland and off of Labrador, coming back as blue, deep water to the south, and getting in around Antarctica and spreading into the other oceans, the Indian spreading into the Pacific, upwelling and coming back. That's the meridional overturning. Meridional, why? Meridional because it's north-south, overturning because it's top to bottom. This circulation is on the 1,000-year time scale. And so we think that it does affect climate. It's interactive with climate. Oceanographers in the North Atlantic are therefore extremely interested in knowing whether it's changing. That's the scenario in Day After Tomorrow. Dump fresh water, slow it down, stop the Gulf Stream, ice age in Europe. Oy. There are a lot of measurements going on to detect any changes here. These measurements are really important. So far, all they show is no trend, a lot of natural variability. It's going to take a long time to pull a trend out of the very, very large decadal variability that goes on in the North Atlantic. So there's natural variability here that masks things. But in the models, on the next slide, the models predict a slowing of this overturn during the 21st century. And that even though it slows, the idea, you know, in these doomsday things is if it slows, then all of a sudden you're not pulling that warm water off of Norway anymore, and Norway will really get cold, much colder than it is now. Because there's global warming, the projections say the temperatures will nevertheless keep going up, just not as fast as elsewhere. That's the source of that little blob in the map that wasn't quite as warm as everything else. It is very, this is you might have heard about abrupt climate change. Abrupt climate change scenarios are often built around changes in this meridional overturning circulation. Shut down ice age. The projections say it's very unlikely that there will be an abrupt transition. I have in my notes down here, I'm not going to write it on here, this is a quote from much farther in the report, just so you don't get alarmist. Global warming cannot create an ice age in any of these projections. No ice age. It's going to warm up. I'd say for the abrupt transitions, there's a lot of weasel wording in the summary about the Greenland ice sheet because it has not been thoroughly understood. And so there may be some abrupt transition due to that. We don't know. 5, oceans and projections of the effects of greenhouse gases and aerosols. If you stop emitting now, you'll still get a warming trend over the next several decades, and that's due to the slow response of the oceans. The oceans are taking up the heat and moving it around, and it's a slow system. So, 10, 20 years to go around a gyre, 1,000 years to go around the whole system. It takes a while for everything to kind of catch up. And lastly, the ocean is becoming more acidic. This is a really easy thing to understand if you understand that if you dissolve carbon dioxide in water, it dissociates into an acid. That's how you weather rocks. That's how you weather limestone. You put carbon dioxide in raindrops. The raindrops become a bit acidic. They're naturally acidic, and they weather the rock. The ocean is absorbing carbon dioxide. There's a really important thing that people are studying very hard. How much of the CO2 gets dissolved into the ocean is a very complicated subject. No matter what, you get an increase in the amount of CO2 in there and an increase in the acidification. There's nothing in here saying what the impact of that is. That's left to Working Group 2. What's the impact on ecosystems? So that's the end of the IPCC summary portion. I'm going to move on to now measurements for observing climate change in the ocean. We need to collect data. We can't stop collecting data. We got models. The models, models need us, observers, to tell them if they're doing a good job. One thing we can say that's said in the summary is that they made projections in 1990 for what the climate would be now, and our observations since 1990 validate those models. They say the models were right. Our temperature increase since 1990 has been what they predicted. The sea level rise has actually been a little bit higher than what they predicted. So we have now a track record. These models were run. We're now running much better models, and we need the observations to continue saying, are those models doing a good job? We measure on the ocean from ships, from autonomous platforms, either things you throw out over the side and drift around, from satellites, and from fixed points like tide gauges. This is the part I do the most. This is from ships. On the left side, there's a ship. That's the Ravel. This is our workhorse instrument. We can profile down through the water column at the bottom, collect water in all those bottles, and analyze them for the chemistry. Important for measuring temperature in the ocean over the many, many decades are these little probes. They're like this big. They look like, you feel like you're throwing a hand grenade into the ocean, but it goes, it just drops. You pull the pin and it drops. And it's going to measure temperature down to about 700 meters. There are millions, well, probably millions of these observations and millions of these little guys on the bottom of the ocean. These are expendable bathythermographs. Any ship can use them. And then the latest addition to the array of measuring, this is a fantastic new program, profiling floats out there going up and down. There's a whole fleet of them now. These are the observations in the ocean that have gone into the heat content estimates. You look at that and go, oh boy, pretty weak. This is the 50s. There's a lot of holes. There's a lot of interpolation. That's why there's error bars. Error bars are based on what you have to interpolate over. This is the modern data set. You still see some big holes in the Southern Ocean. These are ship-based measurements through the 1990s, and the holes are being filled by these autonomous float things. This is a program I've been involved with. These are long lines crisscrossing all the oceans. This happened in the 1990s, and now we're repeating part of it. This is what the U.S. has been doing. Actually, the main U.S. National Science Foundation funded project is here at Scripps. Scientists from all around the country participating. And then NOAA up at PMEL in Seattle. PMEL and NOAA in Seattle doing this. I'm going to show some results from a vertical section right down the middle of the Pacific and a cross section right down the middle of the Atlantic. This one in the Indian Ocean, they just got underway the other day, and there had been some idea of getting a video feed from Jim Swift out there on the ship, but we decided it was just way too complicated. And I should have gotten his picture. Darn. You always think what you want when all I have is this sort of really bland picture of the cruise track so far. New Zealand's under that arrow. They just steamed down. They started in Dunedin on February 4th. They're now at 65 south or so, and they're going to start heading north. Doing this section. Jim Swift's out there. Janet Sprinthal from Physical Oceanography will be doing the northern part of that. These are long, slow, rather boring. You got a lot of work done in your computer kind of jobs. You're out there for 40 to 50 days, punching holes in the ocean, collecting samples. But it's basically adding up to our picture of the world. The next platform, profiling floats. This is a bunch of them. They're out there drifting around 1,000 to 1,800 meters depth, and they surface every 10 days and tell the satellites what they saw. Temperature and salinity. These were developed here at Scripps by Russ Davis, and Dean Remick, who's here, has been absolutely instrumental in getting this whole global observing system off and running. He and Ray Schmidt at Woods Hole together. This is a picture of one being deployed. There it's in its cardboard box that dissolves on impact, and the float goes down and talks to the satellite thereafter. Here's a map of where they are right now. Here's another map. There's 2,788 of them out there, and you can see most of the world is covered except for the ice-covered areas. They're not operating under ice yet. And here's an analysis for this week of temperature from all these temperature observations. And you can get a similar analysis for salinity. Onward, tide gauges. A lot of the sea level information comes from tide gauges before the era of satellite altimetry, which I'll mention next. You need to have fixed tide gauges. They're pretty far and few between, except along the coasts. A lot has to go into interpreting them. Satellites are One of our important ones for climate change is altimetry. This measures the height of the ocean. These are just some big dramatic pictures from NASA showing changes in the sea surface height during an El Nino. I certainly won't go into telling you why it looks that way, but that's an El Nino happening there. This can tell you more than El Nino. It can tell you climate change. And I'll get to a picture much later about that. Sea surface temperature is important. That's measured from satellites as well. And now we'll get into what we observe. Heat content, temperature, sea level, how we get water into the deep ocean, and how salinity is changing and how that relates to changes in precipitation evaporation. This is how the heat content of the ocean has changed. This is based on all those temperature observations. This is from Sid Levitas et al., Ishii et al., and Josh Willis et al. Josh Willis was a graduate student here, was his thesis work. Here it is from 1955 to present. Basically, overall, you could fit a linear trend to that. There's some nice big events to explain in here. We're in the middle of one right now. 3-degree cooling that has yet to be explained. Is the planet losing heat, or are they just not measuring deep enough to see where it's going? These might have been volcanic eruptions. But basically, the heat content has gone up a certain number of joules. Joules is an energy unit. Oh, I can't relate to joules. Okay, a joule. This increase is equivalent to 1/10 of a degree centigrade, which is about 2/10 of a degree Fahrenheit over the top 700 meters of the ocean. So that's measurable. We can see that. This is a graph basically showing that the ocean dominates all of the heat changes in the world. Here's the ocean up here, way off the charts. You know, it determines the size of the chart. Glaciers and ice caps way down here. Continents absorb a little bit of heat. The atmosphere, air, gases just don't hold much heat. Water holds a lot of heat. Sid Levitas calculated that if you took all of the heat in the ocean that's making that 1/10 of a degree change and put it in the atmosphere would be 100 degrees warmer. That's the difference between water and gas. We're pretty happy that most of it's in the ocean. Here's how the oceans have been warming up in a map. You see it's kind of noisy. This is what's being all added up to give that curve. But there's some nice big patterns here. Overall, red means warming, blue means cooling. There are regions that have cooled in the last 50 years. If you know, looking at this map, what the pattern of El Nino is, you would look at that and say, ooh, that looks like persistent El Nino to me. That looks like, oh, the western Pacific is kind of cooling off and the eastern is warming up. That's what an El Nino does. This global warming pattern may have an imprint on natural modes. It may change the phase of things like El Nino. It may put us more in an El Nino mode than we were before. You also see cooling here in the North Atlantic. That has reversed in the last few years. It's been warming. This is work by Sarah Gilley here at SIO, showing temperature changing at 900 meters. That's way down in the Southern Ocean. This change is actually almost 3 degrees over 70 years in some parts of the Southern Ocean, usually more like 1 degree. Most of this warming is because the big current system that goes round and round and around Antarctica, the Antarctic Circumpolar Current, has been shrinking towards Antarctica very slightly, and that allows warm water to move in. So it's not that the warm water warmed up, it's that the whole system shifted. And that shift is associated with a poleward shift, strengthening of the westerly winds, which is a signature of global change. So this we take as a signature of global change, kind of indirect. It warmed up. Why did it warm up? Because the winds changed. Why did the winds change? Well, probably because of global warming. Sea level rise. There's a horrible, horrible table again, but I just want to say, again, 2 bullets. 1, sea level goes up because water warms up, and it goes up because you add water from land ice. Salinity changes can also change the expansion a little bit. You make it saltier or less salty, but that's kind of minor except in some kind of very fresh coastal areas. This is the global average of sea level rise. It looks a lot like that temperature rise, maybe doesn't have quite as exaggerated volcanic bumps in it. There it goes up. This is during the time that we have altimeters measuring sea surface. So this is the best way to measure global sea level. There it goes up. That's equivalent to about 1.5 inches. These are the regional patterns of sea level. I love this picture. I had no clue that it was so complicated. I thought, oh, it's all rising. It's not all rising everywhere. It's rising in some places and falling in others. Blue is where it's going down, red is where it's coming up. This, though, is probably an imprint of big natural modes like El Nino. There's something called a North Atlantic oscillation. There's a Pacific oscillation. There's a southern mode. There are all these modes that have names and acronyms that are natural. That kind of the climate system kind of rings in them. And those all imprint on here. If you add this all up, you get the sea level rise in the previous picture. Mostly this has all this variability because the heating and cooling is not uniform, so the thermal expansion is not uniform. Sea level rise and ice melt, as I mentioned before, only melting of land ice will cause sea level to rise. So when we look at this picture of the Arctic, this melting changes salinity, it changes the reflectivity, the albedo of the planet. That's really important, but it doesn't change sea level. This melting, that's Greenland, would cause sea level to rise. And here's a diagram in the bottom of how sort of the latest ideas about how this is really happening. You have these, this ice sheet, you got some crevasses. Then there's these things called moulins. Moulins? I'm not a glaciologist. I'm going to use a French pronunciation, pseudo-French. It's where the crevasse goes all the way to the bottom, and the water gets all the way down to bedrock. That lubricates the ice sheet and allows it to move much faster than it would otherwise. Here's a picture of a moulin in Greenland. Cheryl Peach said she wouldn't ever stand that close to the edge of that. This is a wonderful slide from Richard Alley, who is a glaciologist and a paleoclimatologist. He gave a video seminar a couple weeks ago, and I asked him if I could use this, and he said, sure. So he talks a lot about how ice sheets are, sort of held up like buttresses by being sort of a ground on rocks and a ground on sediments. If you start peeling off pieces of those, they can slide. You lose the buttressing. So you have, ice is really pretty unpredictable, how it's going to break up. This is his picture, it's not his, it's Craybill et al. And GRL, of how Greenland is changing. Blue areas, it's adding mass, yellow and red is losing. And there's some amazingly fast loss of ice in some of these places that are being monitored closely. Let's go back to the ocean. That's all kind of cool. Sea ice, sea level. If we go back to the ocean, something that's important to look at is how do things like carbon dioxide move into the ocean? Can you get it down there? Because that's going to change how well the ocean can absorb CO2. Changes in oxygen, that might change the ecosystems down deep. Those might be as a response to the circulation changes due to wind changes. Heat content. You add this heat in the surface layer, it's going to move down into the ocean. It's nice to know what the time scale of that is. So just a little tutorial on the circulation of the ocean. How things move in, either they follow the circulation, just go on down, follow your friendly, same friends of isopycnic, same density water. You're going to slide down in with other water that's the same weight that you are. Move on down, or you can diffuse down. Mostly things circulate, but diffusion is important. This map shows a bit of the upper ocean schematic. Doesn't show the whole thing, but you see there are things like these things called gyres that go around. This is the upper ocean circulation in the subtropics. There's equivalent circulations that aren't shown on here in the subpolar regions. The equator has a lot of circulation, etc. It's not all encapsulated there. The bottom one is a fancy version of the meridional overturning circulation, how things go into the deep ocean and move around. And we have two regions where water goes down, around Greenland and in the Antarctic, around Antarctica. We don't get water going down in the northern North Pacific. That's important, has important consequences for what you see when you look at where the stuff goes. Can we track the water from the surface to the deep ocean? We have a really nice tracer, and actually using this tracer was also pioneered here at Scripps. I want to keep telling you what Scripps has done. Use of tracing chlorofluorocarbons, Ray Weiss's lab, freons. These are things that are famous for how they react in the atmosphere and deal, the ozone hole and all that. In the ocean, they don't react. They're just sort of perfect tracers, and you can follow them down into the ocean. So Ray and former students and other colleagues have gotten a global program going. Here's the global inventory of these CFCs. We see a big hot spot in the North Atlantic. The North Atlantic is really vigorously turning over top to bottom in 20 years, filling up the bottom with new water. It's taking CFCs down. You can imagine that's going to take the CO2 with it. All the way around Antarctica, we have a lot of vigorous overturn, upper several hundred meters, lots of CFCs going in. We can look at the ocean cross-cut, and this is finally to some work that I've done. Line right, oops, I can't really, my pointer isn't working all the time. Here's a line down the middle of the Pacific. This is from South Antarctica to Alaska. Where it's dark green, there's no CFCs. There's no freons that have gotten into the deep Pacific. Lots of it in the upper ocean. And you can see it sort of coming down the slopes of Antarctica. So the CFCs are intruding into the deep ocean from the south and the Pacific. If we look at the Atlantic, we see a really different picture. Well, different graphics too, but same colors. There are only a few big areas with no freons at all, and everywhere else we've got freons, especially in the deep North Atlantic. This is the northern end of the section here off of Iceland. Freons way down into the ocean. That's indicating that these waters are no more than 40 or 50 years old, probably less. And you see some invading from the south. So you can see how surface water moves into the ocean. That's going to carry heat and oxygen and CO2 with it. This is a calculation by Chris Sabine and co-workers of the anthropogenic part of the CO2. We dissolve CO2. There's a lot of CO2 in the water, lots of it. They've separated out what part of it is due to us. And it looks a lot like the Freon map, not unsurprising because they use freons to help date the water to get the CO2 that's anthropogenic. But there's a map, big hot spot in the North Atlantic, big ring around Antarctica. Again, that's where the CO2 is going. That's where the acidification would be happening first, although the upper ocean everywhere has a lot of CO2. These are crosscuts to the Atlantic, Pacific, and Indian. Red shows a lot of anthropogenic CO2. This scale is down to 3,000 meters here. There's CO2 way down deep in the northern North Atlantic. They changed scales on us. Here's the Pacific, only to 1,000 meters in the Pacific. So we see intrusions of surface waters. Okay, I want to talk about salinity. Are there going to be droughts? Are there going to be floods? There's a prediction for precipitation changes. But we all can now go look and say, have there been changes in ocean salinity? This is brand new for this IPCC go-round. Brand new results. In a warmer world, we have more water vapor moving around. We would expect the salinity contrast to change in the ocean. Here's what the surface salinity looks like now. Orange is where it's high, blue is where it's low. Orange is roughly where it evaporates, blue is roughly where it rains. Lots of tropical rainfall, lots of high latitude rainfall, lots of evaporation in areas like where we live, all over northern Africa. This is a map of evaporation minus precipitation. Red is where it evaporates, blue is where it rains, net. Okay, messy plots. Probably the most messy ones altogether. This is a plot from south to north of salinity changes in the Atlantic Ocean. And these are added up all the way across from west to east because it's a very noisy signal. This is how salinity changed. If you see a lot of red, that means the salinity went up. So the top 500 meters, the salinity went up. There's also a region where it went down. If you look at the Pacific, you see a lot of blue. Overall, the Pacific is bluer. It's fresher. So if you just added all those things in your mind, the colors, the Atlantic's getting saltier, the Pacific's getting fresher. The Indian is getting saltier. Overall, salinity can't change over the whole world because it's how much salt is dissolved in the water. We're not weathering any faster. There may be a little change in salinity due to melt of ice, of land ice into the water, but that's probably not measurable. Basically, there's a redistribution of salty and fresh water. I'll just show these. This is a cross-section down the middle of the Atlantic Ocean. This is what the salinity looks like. Let's look at the bottom plot. Where it's red, the salinity has gone up. You see way up here at the surface in the evaporation regions, it's gone up. Here in the higher latitude where it rains, it's gone down. And that's actually, you can see that going down is penetrating quite deep. If you add up all the salinity changes in the Atlantic, the whole thing on average is getting saltier. Pacific, same thing. The surface high salinity areas are getting saltier. Low salinity areas are getting fresher. If you added all this up, it would be getting fresher overall. So to summarize, what we're seeing is that salty places are getting saltier, fresh places are getting fresher, more or less, and that might be connected. And it might be a signature of this increase in the hydrological cycle. And the last very little bit, changes in oxygen in the ocean. Oxygen at the sea surface is saturated from the atmosphere. There's lots of oxygen in the atmosphere. Gets into the ocean, and it gets used up by bacterial respiration. In the surface ocean, there's plant life, so actually they're making oxygen. But as the plants and things die and fall, or poop, or whatever, as that stuff falls down into the ocean, bacteria gloms onto it, and you have respiration. You use up the oxygen in the water column. So the older the water, the lower the oxygen. Overall, one might expect the oxygen of the whole world ocean to go down because the atmospheric oxygen is declining, as shown by Ralph Keeling here. But you might also find redistribution in the ocean. If you have faster circulation, so you're bringing in more and more surface water, you see high oxygen. If you're kind of slowing down or moving to warmer water, so the colder water is getting kind of left behind, then you'd see a decrease in oxygen. So changes in oxygen can be a signature of change in circulation also. And I'm going to skip to just some points. I can't lead you through the plots especially. But what we see in the northern North Pacific and the northern North Atlantic is a decline in oxygen pretty close to the surface, 200 to 300 meters down. That's a signature of a change to warmer circulation. And then in the Southern Ocean, a plot, totally inscrutable plot. I'll just tell you what we see. An oxygen increase throughout the southern hemisphere, Central, South Pacific, South Atlantic, Indian Oceans, which one might attribute to strengthened circulation. This is entirely hypothetical still. This is just looking at plots in the last few weeks. And that this strengthened circulation matches the change in sea surface height, which would be caused by strengthened westerlies. This would be a signature of global change. So to summarize, take-home messages for the oceans are changing. There's no question on the very large scale. They're warming, very, very large scale warming. There were some non-uniform patterns in there, but overall it's warming. Overall sea level is rising. Those can't be attributed to anything but anthropogenic change. Salinity changes also reflect a change in raininess, dryness, evaporation, precipitation that would go with the global change. And I think this is an important aspect of global change that people don't fasten on often enough. How much is your rain going to change? How much your water resource is going to change? Oxygen distribution may be changing also. The circulation is changing as the wind patterns change, and the ocean is becoming more acidic. And the very final things, climate change is really here, 90% significance level. No reason to question that anymore. It's important to say that we are already committed to some level of change, even with cutting off emissions now. But with no change in emissions, we are committed to more extremes. So it's useful to look at these plots on your own. And I say that there certainly are things that the IPCC can't address because it's not known science yet. We don't understand the whole climate system, and one of these elements was brought out in the press, this Greenland ice sheet stuff. Necessarily, it's a very conservative report. And I guess I would just like to really say that I really trust the integrity of the process of the IPCC, and I hope you all do too. So thank you.